Welcome to another Cambridge National Award or Certificate in Systems Control Engineering R113 Electronic Principles, and in this video we're going to be looking and talking about semiconductors. If I take you back to the end of the last video, we'd used a potential divider as a sensor. Here we've got two. We've got a light sensor here, the light dependent resistor, where the darkness or the cloud obscures the light, increases the resistance, and therefore increases the voltage across these 2 points, so that the voltage here was increased, triggering some response. And again, here with the temperature, we looked at the NTC, negative temperature coefficient thermistor, and as the temperature dropped, so if we go down in temperature, the resistance increased, and therefore the voltage at this point would drop. So we can have a voltage increase or a voltage decrease, and we used a formula to calculate this, which was R2 divided by R1 plus R2 multiplied by voltage in. And at the end of the last video I mentioned that this output would go into some form of component, and what I want to talk about is how this component helps a circuit act as a sensor to make a decision, if you will, to activate something or switch something on, to act as a switch. Okay, what I want to do to understand this is to look at another circuit very similar to the one that we've looked at before. And this is the potential divider, but I want to look now. The numbers are going to get a little bit more difficult now. From now on, we're going to have to start dealing with some real small values for the electronics that we get in digital circuits. This won't be a digital circuit, but it's starting to move towards this sort of idea of direct current being used as part of digital processes. So I'm going to start with 9 volts here. I'm going to have quite a large resistor, a 1K. 1000 ohms, and we've got a light dependent resistor here. I'm going to set this at, let's imagine that it's quite sunny and the resistance is 100. What we're going to actually do is make it a little bit brighter even, so let's really make it sunny, and we'll reduce that. We'll make that 50 ohms of resistance. Okay, so what would be V out? Now you know how to do this, so I'm going to pause the video here and let you take a minute to do that calculation for me. So hopefully you looked at this and got something like this. We've got R1, which is 50, divided by 1050, I have to excuse the traffic, I've got the window open, multiplied by the voltage in, which was 9 volts, and let's see what that would give us. So that's going to give me quite a small voltage then, 0.4, round it up to 0.43 volts. Now the reason that's significant is I'm looking for a value of 0.7 volts. I'm going to explain a little bit later on why that value is important. But let's just look. We've got 0.43 volts here. Let's look at what happens when the sun goes in. Let's put a cloud here. Let's increase this resistance to 100. And let's do the same calculation. So we've now got 100 R2 divided by R1 plus R2, again multiplied by the voltage in. Let's see what that value is. So 100 divided by 1100 multiplied by 9 volts is going to give me 0.81 volts. So this is less and this is more. Now the component that I sketched out for you in the last video was this component, and hopefully you've gone away and done some research and you'll know that this is a transistor. And to be honest, recognising this one, it's an NPN transistor in this situation. And the interesting thing about an NPN transistor is it forms part of the semiconductor family, and an NPN transistor behaves a bit like a switch. It has a starting value, if you will, of 0.7 volts. And if you apply more than 0.7 volts here, it will actually allow a greater current to flow through here. So we have a small voltage here, will allow a greater voltage here. So it's a bit of a switch because it won't work below 0.7 volts, so it's off, but above 0.7 volts it's on, so it's a switch. Plus, the more voltage you put here, the bigger the arrow here. So it acts as an amplifier, so that you can amplify a voltage within a given region. Now we're going to mostly deal with transistors as switches because there are other components, amplifiers, operational amplifiers, that we'll look at for doing amplification. So how does this actually work? To understand that, first we're going to have a look at another semiconductor, which is a diode. Now a diode symbol is an arrow pointing from positive to negative, the flow of electricity, with a line across it. And I often think of this as a one-way sign, so that it says one way. You can go that way, and this bit here is like a no exit. So you can't go that way, you can only go positive to negative one way. And how this is achieved is by using what's called a semiconductor material, like silicon, part of the silicon chips you may have heard of, and it's basically a material that has a chemical reaction that creates holes on this side and negative charged electrons on this side, and in the middle here is a sort of charged area. It's called the depletion zone, and if you want to get electricity to flow from one side to the other, remembering it can't flow that way, it can only flow, so the positive holes move towards the electrons, if you will, when you attach a battery. So if I just put a battery on there, there's the long side, so that's the positive, there's the short side, that's the negative. Then the holes will travel that way, so the holes can travel towards the electrons, and the electrons can move towards the holes. Bring that up so you can see that. Well, it's this depletion zone that's the important key point here, because it acts as a sort of little wall. So if you put a small voltage through here, you need a certain voltage to pass across or get over this little wall, this depletion zone, and you're probably guessing already that that voltage is about 0.7 volts. Now a diode is useful because we'll look at how a diode works here with regards to working with current. Basically it's very useful in a circuit because it allows you to say, I can let electricity flow in this direction but not, so that way is okay, but that way is not okay. And that can be really, really useful. But the key thing of understanding semiconductors and diodes is that they have this threshold value, if you will, 0.7 volts. And the reason that's important for transistors is a transistor is actually like two diodes back to back. So we've got a diode here going that way and a diode here going that way. So we sort of have two one-way signs pointing at each other, if you will. So you can sort of imagine that being a diode pointing that way and a diode pointing that way. So actually it's saying no electricity can flow this way and no electricity can flow this way. But the key thing about this scenario for the diodes in the transistor is if we apply the threshold voltage, 0.7 voltage plus, then this overcomes this barrier, and actually it allows this to take precedence and we can get voltage through there. So a transistor is basically two diodes back to back, but with a small switch voltage or a small threshold voltage, it will actually overcome that and allow a larger current to flow through. Now, diodes like this have lots of different uses. They're not just one-way directional. You can have a diode which emits light. You'll have heard of these, light-emitting diodes. And later on in the course, we'll also be looking at Zener diodes, which is quite a sophisticated application to do with controlling voltage and voltage regulation. But right now we'll just focus on how this transistor can be useful. So let's take this a little bit further and look at this circuit in combination with the transistor actually being applied to a problem. So if I redraw this circuit now, what we can have is an input, which is a light dependent resistor, LDR. We've got our resistor, let's have 1K there. Let's have our output, if you will, from that, and then we've got our transistor, which actually is a process. So there's some sort of process happening whereby, I've just overdrawn the lines, I wanted to put something in there. Our process is the transistor, so when it receives its threshold voltage we can get, so if you can just ignore that bit there, we can have an output, because we'd have a small voltage here, 0.7 volts plus will mean that we'll get a larger voltage here. So for example we could put an LED there, and when the switch is activated here the LED would light up. So we'd have a light sensor, or this could be a street light, and as it gets darker here this resistance will increase, the trigger voltage will be met, the transistor will switch on and allow a bigger current to flow through a lamp or a bulb. So we could put a lamp in there like a street light, and that would come on when the threshold voltage of the transistor is reached. If we take that application one step further, we can actually look at an exam question, and this is from the Monday the 6th of June paper 2016, where there's an incomplete circuit. And it says figure 3 shows part of a circuit diagram using a 2 transistor combination. Now this is really important. Complete the circuit diagram using a light dependent resistor, an LDR, as an input, transducer, and a signal lamp as an output transducer. Basically transducer is anything that changes one energy into another. So the light dependent resistor changes light into electrons, into resistance, and a lamp changes electrons or electrical energy into light energy. Okay, that's going to be the output there, so I can draw that in. That's going to be the lamp. That's my output. And my input is a light dependent resistor, like so. Remembering, there's the light. Okay, now we've got here, they haven't got their circles around them, but we've got here 2 transistors. And actually, if we look at what happens, we can start to understand. So we know that if we have a cloud here, or if it goes dark, then the voltage, the resistance here, R, is going to increase, which means the voltage is going to increase, which means this transistor will switch on. Call that T1. So that will switch on 0.7 volts. And remember, not only does it act as a switch, but it also acts as an amplifier. So now here we will have a bigger current flowing. Now that current is going to flow around here, and look, that's going to apply itself to the base of this transistor, allowing this to act as an amplifier to allow an even bigger current to flow, which means with a large current flowing through here, this lamp will be nice and bright. This arrangement of 2 transistors gives you a real high level of sensitivity, and it's called a Darlington pair. And it's a bit soppy, but one of the ways I remember it is that the 2 of them working together are like darlings. So they're working together. Darlington pair. So the first one switches on and allows a small current flowing through, which then switches the second one on, which allows an even larger current to go through, which allows the lamp to come on. And this input is the resistance, which increases due to the darkness onto the light dependent resistor. Like that LDR. There's my lamp. There's T1 and T2. Name the 2 components that form a Darlington pair. That is transistors. And then it says here, explain in detail how the circuit works, which we've actually already done. So state what would happen. Sorry, I've got the window open, the traffic going past. State what would happen to the signal lamp if resistor R1 was increased in value. So if we increase the value here. Well, remember, the larger the resistance, the larger the voltage. Now, if we increase this resistance and we therefore increase this voltage, and this voltage has to decrease. And if this voltage decreases on the base of the transistor, then the lamp will go out. So that's what would happen if R1 increases, then R2 would decrease and the transistor would be switched off. So now we have an explanation of how potential divider varies in output, 0.43 volts, passes the threshold to 0.81 volts, activates the transistor. We can see how that can be implied as a light sensor. We've already seen how a temperature sensor could do the same thing and switch transistor on and off. We've seen how that's to do with the fact that it acts like 2 diodes back to back, and that a diode acts as a one-way system to allow electricity to only flow in one direction. And we've understood that the nature of the diode is that it's got holes, or material that's got positive holes on one side and excess electrons on the other, but that there's a barrier in the middle, and that this depletion zone requires at least 0.7 volts for a current to flow, to overcome that barrier, to allow a current to flow. And then we've seen how 2 transistors can work together to act as what's called a Darlington pair, which is a more sensitive arrangement to allow an input, a process and an output. I hope that's been useful, and we'll continue talking about semiconductors in some of the later videos.